So there is many different ways in which you could measure the purity of subsets, lots of different ways to define it. A pretty good way to define it is with something called entropy. So here's the definition of the entropy. P plus is the percentage, the proportion of positives in a subset. P minus is the proportion of negatives in a subset. And the way you're combining them is you're saying P plus log P plus minus, P plus log P plus plus P minus log P minus, and then you negate the whole thing. Seems like a strange formula, but it actually has a nice interpretation that we'll go over. Now, keep in mind, the entropy, it's specific to a subset S, and the P plus and P minus are the proportions of positives and negatives in that subset, not in your overall data set, just in the subset where you're trying to measure the purity. So entropy has an interpretation. If your logarithms are base 2, then you can interpret this whole quantity as effectively the number of bits that allow you to overcome uncertainty about whether an item is positive or negative. So the way to think about it is, suppose I have a subset with a certain entropy. Right? Now, you pick a random element from that subset. How many bits do you need to determine whether that element is positive or negative? Right? So if the subset is completely pure, you don't actually need any bits. Right? If the subset is all positive, you pick any random element from the subset and you're guaranteed that it is positive. So you don't need any bits to determine whether it's positive or negative. You know that it's positive. On the other end of the scale, we have a 50-50 subset, right? Half the items are positives, half the items are negative. You pick a random item. Does the subset tell you anything about that label? No, it tells you nothing. So you have no hint whatsoever about whether that's positive or negative. So you would need a full bit to decide if it's positive or negative, right? A full bit would tell you it's 1 if it's positive or 0 if it's negative. So those are the endpoints. And in general, for different proportions, it'll assign a different number of bits. So here's an example. We have a totally impure subset, 3 yeses, 3 no's. The entropy for that is log of 1/2. And it's basically the same thing. It's just log of 1/2, and it's base 2 logarithms. So base 2 log of 1/2 is just -1. It's the power to which you need to raise 2 to get 1/2, and it's -1. So you have -1 here, you have -1 here. You average them, you still get -1, and then you take the minus sign in the end, and you end up with a 1. So you need 1 bit to tell whether an item in a completely 50-50 subset is positive or negative. For a totally pure subset, this is what you get. So you get 4/4, that's 1, and log of 1 is 0. And here you get a log of 0, but which would technically be -infinity, but you're multiplying it by 0, so that cancels out. So you end up with having 0 bits. So totally pure set, you need 0 bits. Totally impure set, with 2 classes, you need 1 bit. And for different values, for different proportions, you get numbers between 0 and 1. So it's a little bit weird to think about fractional bits. Right? So what does it mean? What does it mean to have a 0.33 of a bit? It's hard to think about that, but basically what it says is that it quantifies the uncertainty. It tells you how uncertain you are about whether a randomly picked item is positive or negative. And it has very low values at the ends. So if the set is pure, whether it's totally negative or totally positive, you get an entropy of 0. When the set is fully balanced, 50% positive, 50% negative, you get the highest value for the entropy of 1, and you get values decreasing towards the endpoint. So anything in the middle is going to have smaller entropy. So It seems like a pretty complicated measure. It's actually a really good measure. And what it does is it gives higher numbers to subsets that are less pure and lower numbers to subsets that are better separated in terms of positives and negatives.